Let's talk about the efficiency of binary search tree operations. For searching, insertion, deletion operations, we compare the search key we are looking for to the search keys in the nodes on the tree along a path through the tree. The path terminates at the node that contains the search key, or if the search key is not inside, or at empty subtree. The time complexity or efficiency is based on the number of comparisons or number of nodes along the path. Because it is binary search tree, the maximum number of comparisons is the number of nodes on the longest path, which is the height of the tree. The maximum height of a tree which contains n nodes is n when the tree is screwed, which is a linked list. For complete tree or full tree, they have minimum height. The height will be log base 2n. For example, if we are looking for 4, we compare 4 with the row node item 6. It's 4 is smaller, so we go left. And then compare 4 with 2. 4 is larger, we go right subtree. And then we find 4. So the search is confined to nodes along a single path through the row to a leaf. The search time will be big O, the height of the tree. If the tree is balanced, which means the minimum path length is close to the maximum path length, which is log n. So for balanced binary search tree, the searching time complexity will be big O log n. N is the number of nodes. Suppose we want to insert number 5 into this binary search tree. We compare 5 with the row node item 6. 5 is smaller, so we go to the left. And then compare with 2. 5 is larger, we go to the right. And then we compare to 4. 5 is larger, we go right. So right is empty. We insert, create a new node, contains 5 and touch to the right side of node 4. What's the time bound for insertion? 5. Certainly, we go along one path, find the right location for 5, and then to create new node, and then touch to the right side of node 4. The time complexity is composed of two parts. One, searching, which is big O log n. Next one is create a node and then touch to the right, which takes constant time. Therefore, the insertion time complexity will be big O log n if the tree is balanced. For binary search tree deletion, it takes the same procedure, and then the time complexity will be similar for insertion. Let's make a summary. For retrieval or searching, insertion, deletion on binary search tree, for normal case or called average case, the time complexity would be big O log n. The worst case, if the tree is unbalanced, and the time complexity will be big O n. N is the number of nodes in the tree. For traversal, you have to visit every node, so the time complexity will be big O n. N is the number of nodes. Two questions. In which order of a set of data? When we perform insertion, it will produce a maximum height of binary search tree. In which order we'll do insertion, and then we can produce a minimum height of binary 33.